Hello everyone. Have you ever wondered whether an antenna can change its operating frequency, radiation pattern, or even its shape without being physically replaced? Traditional antennas are usually designed for a specific purpose, but modern communication systems demand much more flexibility. In this presentation, we will explore an exciting advancement in antenna technology known as liquid dielectric reconfigurable antennas. We will see how liquids can be used to create smart antennas that adapt themselves for future wireless communication, defense applications, and even emerging 6G networks. Let's start by understanding the problem. Every year, wireless systems become more advanced. A single device may need to communicate over multiple frequency bands, perform sensing, support navigation, and even participate in radar operation. Traditionally, this would require multiple antennas, but adding more antennas increases size, weight, complexity, and cost. To solve this problem, engineers developed reconfigurable antennas. These antennas can perform multiple functions using a single structure. Initially, technologies such as pin diodes, RF MEMS, and varactors were used for reconfiguration. However, these methods have limitations such as narrow bandwidth, complex circuitry, and high operating voltages. This led researchers to explore a completely new idea, using liquid dielectric materials to achieve antenna reconfigurations. Imagine a military communication system operating in a rapidly changing environment. One moment it needs long-range communication. The next moment it may need radar functionality or beam steering. Using separate antennas for each function is inefficient. A reconfigurable antenna can switch between different functions within a single structure. It can change its frequency, radiation pattern, polarization, or beam direction depending on the requirement. This flexibility makes reconfigurable antennas highly useful in satellite communication, wireless networks, radar systems, imaging systems, and future intelligent communication platforms. There are several methods available to reconfigure an antenna. Electrical reconfiguration uses components such as pin diodes and MEMS switches. Optical reconfiguration uses light control switches. Physical reconfiguration changes the geometry of the antenna itself. Material reconfiguration uses special materials whose electromagnetic properties can be controlled. Among all these techniques, liquid-based reconfiguration has recently attracted significant attention because liquids can easily change shape and volume. Before discussing liquid dielectrics, let's look at liquid metals. Liquid metals behave almost like conventional conductors while remaining flexible. This makes them ideal for wearable electronics, flexible devices, and stretchable sensors. Unlike rigid metallic antennas, liquid metal antennas can bend and adapt to different shapes. This flexibility is an important advancement. However, liquid metals can be expensive and may have practical limitations. As a result, researchers started exploring another category, liquid dielectric materials. This slide highlights why liquid dielectric materials are attracting so much research interest. The first advantage is conformability. Since liquids naturally take the shape of their container, antennas can be designed in almost any geometry. The second advantage is reconfigurability. Simply changing the liquid level or composition can alter the antenna characteristics. They are also relatively inexpensive compared to many advanced materials. Some liquid dielectrics are transparent and biocompatible, opening possibilities in medical and wearable technologies. Finally, their high permittivity helps reduce antenna size while maintaining performance. Whenever a new antenna technology is developed, engineers need a way to evaluate its performance. One important parameter is frequency tuning range. This tells us how much the antenna frequency can be changed. Another parameter is total spectrum coverage. This indicates the overall range of frequencies that the antenna can support. The tuning ratio measures how effectively the antenna can switch between operating frequencies. Together, these parameters help determine whether the antenna is suitable for practical communication systems. Most liquid dielectric antennas belong to a category called dielectric resonator antennas, or DRAs. Traditional DRAs use solid dielectric materials such as ceramics. These antennas are known for high efficiency, compact size, and excellent performance. Researchers discovered that replacing the solid dielectric with a liquid dielectric introduces a completely new capability, dynamic reconfiguration. By simply changing the liquid volume, the antenna frequency can be adjusted. This creates antennas that are easier to prototype, highly adaptable, and capable of taking almost any shape. This slide shows one of the simplest liquid dielectric antenna designs. At first glance, it looks like a transparent container filled with water. But this water is actually functioning as part of the antenna. The central probe excites electromagnetic waves inside the water column. Now comes the interesting part. If we increase the water level, the effective electrical length changes. If we decrease the water level, the antenna behaves differently. This means the operating frequency can be tuned simply by changing the amount of liquid. Imagine adjusting an antenna's frequency not by replacing hardware, but simply by controlling the liquid level. That is one of the most fascinating advances in this field. This slide demonstrates an important concept. Even if the liquid remains the same, changing the way energy is fed into the antenna can dramatically alter performance. Researchers have experimented with top-loaded probes, cone feeds, spiral feeds, ring feeds, and slot feeds. Each feeding method influences bandwidth, radiation pattern, efficiency, and polarization. You can think of the feed as the engine that drives the antenna. Different engines produce different performance characteristics. This research has shown that innovative feeding techniques can significantly improve the capabilities of liquid dielectric antennas. This slide showcases one of the greatest strengths of liquid dielectric antennas, the freedom of shape. Because liquids adapt to their containers, researchers can create many different antenna geometries. Helical antennas can be formed using flexible liquid-filled tubes. Compartment-based antennas can tune frequency by controlling liquid distribution. Transparent patch antennas can be constructed using water. Some designs can even steer beams or switch polarization. This level of flexibility would be extremely difficult to achieve using traditional rigid antenna structures. This is where liquid dielectric technology begins to look like a truly next-generation solution. Now let's see why defense organizations are interested in this technology. Modern defense systems require communication equipment that can adapt quickly. A battlefield radio may need to operate at multiple frequencies. A radar system may need different radiation characteristics. A drone may require lightweight and adaptable communication hardware. Liquid dielectric reconfigurable antennas offer the possibility of achieving these functions using a single adaptive antenna system. This can reduce hardware complexity while increasing operational flexibility. As communication systems move toward 5G, 6G, and beyond, antennas must become smarter. Future networks will require dynamic spectrum access, beam steering, intelligent communication, and adaptive operation. These are exactly the kinds of capabilities offered by reconfigurable antennas. Although liquid dielectric antennas are still largely in the research stage, they represent a promising technology that could support future intelligent wireless systems. To conclude, liquid dielectric reconfigurable antennas represent an exciting advancement in antenna technology. They combine flexibility, tunability, and adaptability in ways that traditional antennas cannot easily achieve. While challenges such as switching speed and practical implementation remain, ongoing research continues to improve these systems. I encourage you all to keep learning about the latest advances. Thank you for your attention and happy learning.